Thank you very much. Good morning, everybody. And also I would like to thank the organizers for the invitation and for this nice conference. Okay, so I should warn you that I'm not a topologist. So I'm doing a representation theory. And the subject of my talk will be cluster algebras and categorification. And, well, since I'm speaking to topologists, I decided to restrict my talk on cluster algebras associated with triangulated surfaces. So this will be my first talk. And since I assume that you don't know anything about cluster algebras and also nothing about representation theory, so this will be more a colloquium than a course. Okay, so yeah, talk one will be on cluster algebras. And talks 2 and 3, I will speak about categorification. Okay, so yeah, let's start with part 1. So first, I will start with a very basic fact that you may know about triangulations. So here it's really I'm following the paper of Fomin, Shapiro, and Thurston in 2008, and yeah, probably I should also cite for Goncharov, but this part I won't speak so much because this is too much geometry for me. So we will start with sigma, and sigma will be an oriented Riemann surface with non-empty boundary. And I will fix a finite set of marked points on the boundary. So I will tell you later that this is a big restriction, so we can also assume that we have some punctures that are marked points in the interior of the surface. But for my talk for today and for the rest, I just restrict here. I think it's interesting enough somehow and much easier. And I assume that there is such that there is at least one marked point on each boundary component. So for each boundary component, B, so okay, so this is the setup, and now I can define the notion of arc. So gamma, an arc will just be a continuous map on the surface. So this will be an arc, and we assume that gamma 0 and gamma 1 are in M. We also assume that the arc does not intersect, so but we may have gamma 0 equal gamma of 1. And we will also assume that gamma is not isotopic to a point or to a boundary segment so it means that if this is d sigma, and so this is not an arc, and this is not an arc, but this is an arc. Okay, so this is an arc. So a boundary segment, I mean, I don't have to define, I guess you understand what this is. And we consider the set of arcs up to isotopy, and yeah, maybe I should write it here. So I will denote by A sigma M the set of arcs. Okay. So now I can define what, if I take two arcs, we say that they are compatible if there exists a representant in the isotopy class that do not intersect. So if they do not intersect, except for maybe the endpoints. And so what is a triangulation of my my surface sigma? So triangulation is a maximal collection of compatible arcs. Okay, so yeah, just start with very easy examples. So
this can be sometimes empty.
What?
Triangulation. For instance, if you have a disk and just one.
Yeah. So yeah, I should have said that I assume that my surface is big enough to have such triangulation. So I just, I don't want a disk with just one mark point on the boundary, or two, or even three. I assume that there is at least 5 points on the boundary for a disk. And yeah, but except in this situation, there always exists a triangulation.
If you have a homogeneous surface, do you need to require that you have a large enough number of points so that they're spread up into triangles? Or?
No.
And she has the hypothesis B into M and non-M.
Yeah, I assume this.
And there has to be boundary.
There is boundary, so if you take a torus with one boundary component and one mark points, then you have, so yeah, maybe if you take the torus and say 1 mark point on the boundary. Okay, so this, yeah, maybe I should put some colors. Yeah, so this will be a triangulation, for instance. Okay, and yeah, an easier example, if you take an hexagon, this will be a triangulation. And okay, and this will be a triangle, and this, I will call this an internal triangle if the three sides are internal arcs and not boundary segments, and as in this situation. Okay, so now maybe very basic facts on triangulations. So so first of all, triangulation exists except in the situation where you have a disk with less than 4 marked points, and the number of arcs is always the same. So yeah, if and yeah, the number of arcs is always 6g minus 6 plus 3b plus c. So g is a genus. B is the number of boundary components, and c is just the number of marked points. Okay, so this is just an easy computation of a Euler characteristic. And the second thing is that you have a notion of flip of a triangulation. So for any I, so there exists a unique tau I star, which is not isotopic to tau I, such that if you replace tau I by tau I squared, you get a new triangulation. And yeah, so here also you have to accept the situation. Yeah, so sigma is not a disk with 4 or less marked point. Okay. And yeah, so the picture is really easy. So if so, this is the arc tau I, and these are the two triangles that could be the same triangle, but you have these two triangles. here, and so this is tau I star, and this will be, so this is a flip at tau I of the triangulation. So if I take, so let's say I want to flip this arc in the torus situation, so what I will get will be okay, so this will be the flip of my arc here. Yeah, and the last basic fact I want to tell you is the following. So, for any two triangulations, tau and tau prime can be related by a sequence of flips. Okay, this is really just the thing I wanted to say about triangulation, so very easy and basic facts. So now I can start with cluster algebras. So this will again be based on the Fomin-Shapiro system, but also on Fomin-Zelevinsky first paper on cluster algebra. So yeah, I should say that Fomin and Zelevinsky they introduced the definition. So yeah, maybe it's 2002. The definition of cluster algebras, but really this cluster algebras in this triangulation context, it's really in this paper by Fomin-Shapiro system. So yeah, I will start with the main theorem of this talk. So it's a kind of mix of these two works. So let sigma m be and tau be a triangulated surface and the number of arcs of the triangulation, and so there exists a map that I will denote by x tau from the set of arcs to the field of the rational function in n variables. So I will denote this by x underlined. So such that so first of all, x tau of tau I is just xi, and secondly, so for any a, b, c, d, e, f arcs in the following configuration. So A, B, C, D, E, and F. So if you just take these 6 arcs in that configuration, then we have the following relation. So x tau of E, x tau of F is just x tau of A, x tau of C, plus x tau of B, x tau of D. Okay. So, which is a very natural relation if, well, this is a Ptolemy relation. So if you take 4 points on a circle, then you have the following relation for the different lengths.
Sorry, I have a question. E and F seem to intersect there, or is it just a schematic picture?
No, they intersect.
They intersect?
But they are not, I mean, they are arcs, but they are not compatible arcs. I mean, and just, so I could have said for any such configuration, for any triangulation, if F is a flip of E, then you have such relation. So then if you, I mean, with this result, if you combine this result with the previous one, you can easily describe this map just starting from the initial triangulation, and then you apply flips, and since all arcs are, maybe I should have said that any arcs is part of a triangulation, can be completed in a triangulation. So you take any other arc, you put it in a triangulation, there exists a sequence of flips, and then you apply the sequence of flips, and you get the different values of this. But of course, this sequence of flips, is not unique at all. So this is the point of the theorem, that whatever sequence you take, you will get the same value of for your for the map. Yeah. So.
Just a stupid question. It is all the time. It is A, B, C, D. It is a disk, or it could be with genus inside. Or...
No. It's well. This is not on the disk. This is whatever.
Maybe there is also an F prime which has the same.
No.
I mean, there is F, but I can also picture an F prime which is not isotopic to F.
No, there is a unique F in this configuration, because the flip is, well, I mean, you have this notion of flip, so if you remove E from your triangulation, there exists only one, and so F is entirely defined by this picture. If you know A, B, C, D, E, you should know F.
So these are two triangles?
Yeah, these are just two triangles of your triangulation that are,
So there is this.
Yes.
Okay.
okay, yeah, locally it's a disk.
Okay, locally, yes.
Yeah.
That's my question.
But there may be identification.
But you may have A equal C, for instance. You may have A equal C and B equal D, for instance. But yeah, and I should say, of course, in this picture, you may have some arcs that are not arcs, but boundary segments. And then it's just, you put x tau of alpha is 1 if alpha is a boundary segment. Okay.
The map style is uniquely determined by this condition.
Sorry?
The map style is uniquely determined by this condition.
Yeah, so then the map x tau is uniquely determined by this condition, but it's not clear that it is well defined. So this is the theorem. Okay, so I will continue with an easy example. So, yeah, I will just take the easiest example. So just take a pentagon with, so this is tau, so with these two internal arcs, and I put x1 here for this internal arc and x2 here. And then I will just flip these arcs to get, well, so in this case I have only finitely many arcs, so it will be kind of easy. So if I just flip this arc, what I get will be the following picture. So this will be and yeah, it's easy to, so then what you get is, so the x tau of this arc will be 1 plus x2 over x1. Okay, because you just have to multiply these two, so x2 by 1 and 1 by 1, and then you divide by x1. So this is what you get for this arc. And then you can continue. So if I flip this one, I just go back here. So I have to flip this one. And then I will get this arc. And this, for this arc, what I will get is just and this is, yeah, maybe let me just, to be sure I'm not writing anything wrong. So it's just, you can check that you get this. So then we can continue and so for this red arc, I will get 1 plus x1 plus x2 over x1, x2 divided by 1 plus x1 divided by x2. And here you have a sort of a miracle. And you can check that what you get is 1 plus x1 over x2. And if you think about it, I mean, if you just have, yeah, you can just, in this picture, if you just flip x2, you will get this red arc. And if you just flip x2, this is a relation that you would get. Okay. So here. Okay. And this phenomena just appear always. Okay, so in this situation, you. Oh. What?
What's missing?
I mean, you don't have all the triangulations, but you have all arcs on the blackboard. I mean, this is a.
Are you sure on the?
Yeah, okay, this is not F2, sorry. Yeah, this is not F2. I mean, I should have said. So this would be F2, so. And then, but I mean, what just interests me is the value of this arc, and this will be, and so here you again have a flip. So, okay, you have the following picture. Okay. Yes?
I think 1 and 2 are swapped in the denominator and in the fraction time. So you must divide by 1 plus x2 over x1 and get what.
Oh, right. Yeah, I should divide by this one. You're right. Thank you. Yeah. Yes. Okay, thank you. And yeah, what you. No, but this is correct. This is correct. You get the other one. Okay. Yeah, so maybe I will give you another example. So just take yeah, it's not at my paper here. So just take an annulus. So a disk with two boundary components. So I just draw it like this, and I identify these two arcs, and I take the following triangulation. Yeah, and I take 1. So okay, b equals 2, g equals 0, and c equals 1. And I take the following triangulation. So here I have only 2 arcs again. And if I flip, so here I can flip and flip at x1, and then x2, and then x1, and then x2. And so, okay, first, if I flip x1, I will get a new arc, and the corresponding x tau of this arc will be 1 plus x2 squared over x1. And I can continue this, and you can easily check that you have, yeah, so just call this x3, and that you have the following inductive relation that, yeah, so for k in z. And so here, well, you may recognize as a sum of sequence. And yeah, maybe I will tell you this recursion a little bit more about this later. Okay. So using this theorem, I can give you the definition of cluster algebra in this context. So let me check my paper. Which is due to forming the Levinsky. So, a cluster algebra associated to sigma m, well, I don't write m anymore, but sigma tau, is the subalgebra of z of x generated by x, the image of x tau. So this little bit of terminology. So this x tau of gammas are called cluster variables. And if you think of this topological site, we can put them together in sets corresponding to triangulations. So so if you take n arcs that are compatible, you can then gather these variables into sets, and these sets are called cluster. Okay.
By condition one, x tau of tau I is xi. So I don't see how this algebra is different from the.
What did you
It
say?
contains more. In this example, you can see it also contains 1 plus x2 over x1.
Yes, but no, it's oh, okay.
Triangulation tau in the cluster is just.
Yeah, but yeah, so here I take any other triangulation, not only tau one. I mean, you mean the cluster? No, I don't.
For each
Get-
triangulation, you have a cluster.
So the,
For tau, you have a very simple one.
okay, yeah, so maybe I will tell you this in a moment. I mean, this map x tau is injective, so this can be proved. So then you get a bijection between triangulation and clusters.
The gamma 1 till the gamma n is the given tau triangulation? Or is another definition?
It's any triangulation. It's not tau. It's not necessary. I mean, okay. So then, of course, x1 up to xn is a cluster, and it's called the initial cluster. But you have many others. Yeah. Okay. So this map is injective, and also one can show that. So then. Yeah, what one can show that using this that this algebra has finite type if and only if you have finitely many arcs, which means sigma is a disk, or in other words, if and only if the mapping class group of sigma and so you don't ask, so this mapping class group is just the mapping class group, but you don't want to be identity on the boundary, but you just want to preserve the set of mark points globally. So it's, but it's a finite group. Okay, so in the disk situation, of course, what you get is just an abelian finite group. And also what we have is that if you take another triangulation, so let's take tau prime is tau 1 up to tau n. So if you take a cluster, no, x tau of tau prime of A, x tau of tau prime of n is a transcendental basis of z of x, and then it means that oh, right, yeah, here I have two primes. And, okay. Yeah, so here you get an isomorphism, and if you just restrict to so if you take two triangulation, you can form another cluster algebra of the same surface, and in fact this gives you an isomorphism of cluster algebras, well, of algebras, but also, but this is not identity map. It's just so here you will send xi to no, I'm lost, but I mean, you can guess what the maps are. Okay, so let's come back to my. Okay, maybe I will just come back here. Oh, sorry. Okay, maybe just I will give you another example which you can see as an exercise. So if you take an hexagon with the following initial triangulation, you will get 9 cluster variables, which are so x1, x2, x3, and the last one is x1 plus x1, x2 plus x3 plus x2, x3 over x1, x2, x3. Okay.
Which edge is the last one? I mean, there seems to be unique, most complicated one. Which edge?
No, you don't have necessarily one most complicated one, but so this one, so maybe as you will see later. So first you have always, these are Laurent polynomials, and the denominator is, well, it is not always the case, but almost. This will be the number of crossing of the arc respect to the triangulation. So this one crosses the arcs 1, 2, and 3, so this is just this arc. But so if you start with this triangulation, so you won't get one most complicated cluster variable. Okay, so so now I will just tell you different theorem. So of course without any proof or whatever. So the first theorem is exactly this Laurent phenomenon that you can see in this example, that always occur, and so which is a theorem due to Fomin and Zelevinsky in their first paper. And I mean, it's not clear from the definition. You can see in the computation that you have somehow to divide by, so if you see the last cluster on cluster variable on the blackboard, you have to divide by x plus 1 plus x2, so it's kind of a miracle that the fraction just simplifies. Okay, so theorem by Fomin and Zelevinsky. So it's just that called the Laurent phenomenon. So for any arc, x tau of gamma belongs to this algebra, and of course, as a corollary, if you combine with this bijection, you get that x tau of gamma will belong to any. You can express it in as a polynomial as a rational function in any cluster, and this will be this will again will be a Laurent polynomial. So for any cluster so then you get that this algebra is a subset of this intersection. So you can take the intersection of any thing that can be written as a Laurent polynomial in any cluster, and you have this inclusion. And in general, well, so this is an important set in cluster theory. This is called the upper cluster algebra. And so it's not, well, often, I mean, in some cases you have equality, in some cases you don't have equality, but it's not an easy question to check whether you have equality or not. So you have another theorem which is really important, which is called the positivity, well, conjecture first. So it was just stated by Fomin and Levinsky in their first paper, and then you have several answers. So in this context of triangulated surfaces, it has been proved by Mazeker, Schiffler, Williams in 2011. And well, you have a more general proof by Lee Schiffler in 2013. You have also a paper by, but so here the proof is totally different, and using algebraic geometry and hacking. Kiel, Kontsevich. And I think it's 2015. Well, you have, and maybe, I don't know whether I should put for Gonchar for this positivity conjecture, maybe. Also, I mean, lots of people have worked in this, and this is just stating that for any gamma arc, x tau of gamma can be written with positive coefficients in terms of the initial cluster. And yeah, so you can check it on the example. And I mean, it's not just a remark, because you may think that in this cluster relation you have only positive coefficients, so somehow but it doesn't mean that this is immediate theorem. If you just think that so this is not in n of x. Okay, so since you have simplification, it's not clear, because you have only positive coefficient in your fraction, it's not clear that at the end you have only positive coefficient. So this is just a remark. Okay, so, and yeah, the last thing, I mean, among the main question about cluster algebras, one, maybe the biggest question is about the existence of bases. And so here again you have lots of work, and yeah, I could cite the same guys and also a lot more, but yeah. So this is a very difficult question, and you have different answers to, and yeah, this covers, you have some different kind of basis you want to find, but I will speak later a bit more about this question. So in the last 5 minutes, just one remark about this. So about the positivity conjecture, if I come back to this example, so if you, in this relation, if you put x1 equal x2 equal 1, if you put the initial condition x1 equals x2 equal 1, and you take this relation, so it's a very old problem, this sum of sequences, that xk is always an integer with, well, a positive integer. And actually you can see the link with this positivity conjecture here. Okay, so I will just end my talk with generalizations So I was expecting more time, but okay. Okay, so this definition of cluster algebra is, as I told you at the beginning of my talk, this is a very, very restrictive definition of cluster algebra, but I think yet so you easily see the motivation and the fact that this algebra can be seen as a natural object to consider. And you have lots of generalizations. So the first one is, of course, that you can add some marked points in the interior of the surface. Okay, so okay, so the first natural generalization is just to add marked points in the interior of the surface. And here it becomes a little bit more tricky because this fact that you can always flip, it's not true anymore. Because typically if you have such configuration, so this is triangulation, you flip this arc. So what you get is, well, a kind of strange triangulation. You will get this. And so this is a strange triangle, but well, we can still say it's a triangle. It's a self-folded triangle. But then if you want to remove this arc, then you cannot flip. So this is the main thing of this paper by Fomin, Shapiro, Thurston. They introduced the notion of tagged arc in order to be always to always be able to flip arcs. So this is the first. But then all the rest of what I say is true, and except that this Ptolemy relation becomes just a little bit different in this situation, but it's okay. So the second generalization is to, or is that what one, so we will see it in the second talk, but one can associate a quiver to tau. So a quiver is just an oriented graph. I will speak a lot of them in my last talks. And then the flip can be translated in an operation on the quiver, which is called the mutation. But, and then you can somehow start with any quiver. And of course, if you take a triangulation, you won't get any quiver. So you can start with a very, very general situation of starting with any quiver and perform this mutation process. And then you get this algebra, but you don't have this topological meaning, but still you have all these properties. And yeah, so here I should send you on a so if you want to see what this quiver mutation operation is, you can just put quiver mutation in Google, and you have a very nice applet due to Bernard Keller, and it's a Java applet, and you can play with it, and you can, well, guess what's the rule. Okay. Yeah, maybe I have 1 minute, or it's, yeah. Okay, so if you want to be even more general, you can, so a quiver, so this will be a quiver without loops and without two cycles. And to such quiver, you can associate a skew symmetric matrix just the incidence matrix of the quiver, and in fact you can replace this by, so you get an algebra, a cluster algebra for any skew symmetric matrix with integer coefficients, and you can replace this setup by any skew, well, first skew symmetrizable matrix, and even you can take a matrix which is not a square matrix, and well, so you have lots of generalization, and so these are cluster algebras with coefficients. And finally, just a few words about all these cluster algebras. So as soon, well, more or less, as soon as you have a relation which looks like a Ptolemy relation, you should have a cluster algebras which is hidden somewhere. So for instance, if you take, so in SLN you have this kind of relation, so you can take the algebra of, the coordinate algebra of, on SLN, and if you take the minor as a coordinates, you have this kind of relations. You also have this kind of relation on the Grassmannian. So if you take this Grassmannian of planes in Cn, and you take Plücker coordinates, you have also very similar relation as a Ptolemy relation, and it means that somehow the algebra of coordinates has a cluster algebra structure. And you also have, so here I should cite Fock and Goncharov, you have this decorated Teichmüller space, and with planar coordinates, which corresponds to 2 lambda lengths, and you have this Ptolemy relation, and then it means that somehow, so this is a cluster variety, and you take the algebra, and you get a cluster algebra. Okay, thank you very much.